Welcome to our video on the physics of elementary particles. Here we will discuss conservation laws. All particle interactions conserve energy, momentum, and angular momentum. Take this for granted and let us concentrate on the other conservation laws: electric charge, baryon number, and lepton numbers where 1 is for all leptons, and further 3 lepton numbers consider the generations electron, muon, and tau. Electric charge is conserved even with the fractional charges of quarks. Let us consider an example of a charged weak interaction process where a positron and a d quark exchange a W boson. With this interaction, the positron becomes an anti-electron neutrino and the d quark a U quark. Sum up the electric charges before and after the interaction. On the left, the positron has elementary charge 1. Subtract the 1/3 negatively charged d quark to get plus 2/3. After the interaction on the right, we have the neutrino with 0 charge and the U quark consistently with plus 2/3 elementary charge. Thus, electric charge is conserved, everything is okay. Let us understand baryon number. Baryons are hadrons made of 3 quarks, and the big idea is simple and joyful. If you begin with a baryon, you end with a baryon. To cope with a baryon like the proton, we assign it the baryon number 1. An antiproton has baryon number -1. Pions are classified mesons. They have a quark-antiquark pair. Mesons have baryon number 0. In the process shown, the lambda baryon decays to proton p plus pion pi minus. The next line says b equals 1 goes to b equals 1 plus 0 equals 1. We read it like this. The initial lambda baryon has baryon number b equals 1. In the final state, the proton contributes b equal 1, while the pion contributes b equals 0. The sum stays 1, so baryon number is conserved. Now a scattering example. Pion plus proton goes to neutron plus proton plus antiproton plus pion. The second line tells us b equals 0 for the pion plus 1 for the proton equals 1. This goes to b equals 1 for the neutron. Plus 1 for the proton minus 1 for the antiproton plus 0 for the pion equals 1. Initially and finally, the baryon number is 1. Even with particle-antiparticle production, the total baryon number stays constant. That is a powerful conservation law. Now, lepton numbers. In addition, for an overall lepton number L, we track for each lepton generation a separate number, so-called lepton flavor numbers. Flavor refers here to the 3 generations of leptons: Le for electrons and electron neutrinos, L mu for muons and muon neutrinos, and L tau for taus and tau neutrinos. In this scattering process, the electron plus the proton go to electron plus neutron plus positive pion. The next line states that the electron flavor number is conserved. The incoming electron carries Le equal 1. The incoming proton carries 0, so Le equals 1 before scattering. After scattering, the outgoing electron still carries Le equal 1, while the neutron and the pion carry Le equal 0. The total electron flavor number Le stays 1. In this muon decay, the positively charged muon goes to positron, plus electron neutrino, plus muon antineutrino. Then we consider 2 flavor number checks. First, the muon lepton number L mu. The initial anti-muon carries L mu equal -1. In the final state, only the muon antineutrino carries L mu equal -1, while the positron and the electron neutrino carry L mu equals 0. So L mu is conserved. Second, the electron lepton number Le. Initially, there is no electron flavor. After the decay, the positron contributes Le equal -1, and the electron neutrino contributes Le equal +1, while the muon antineutrino contributes Le equals 0. The sum is 0, so the electron flavor number is conserved too. Flavor conservation works generation by generation here. Finally, total lepton number. The equation shows a hypothetical process that has never been observed yet. Mu minus goes to E plus E minus E minus, a decay that experiments search for to test lepton number and flavor conservation. Here's the idea. The initial mu minus is a lepton with total L equal +1. The final state would contain 1 positron with L equal -1 and 2 electrons with L equal +1 each, so the total L would remain +1. However, this decay would violate lepton flavor numbers because it turns muon flavor into electron flavor. Experiments have pushed exclusion limits for this decay to below 10 to the minus 12 in branching ratio, making it extraordinarily unlikely. However, here is one more cheerful note. In neutrino oscillations over large distances, electron neutrinos from the Sun can transform into muon neutrinos. In these oscillations, the total lepton number L stays conserved, while here individual flavor numbers like Le and Lmu do not remain fixed. We discussed various conservation laws where energy, momentum, angular momentum, and electric charge are conserved also in particle physics. We learned about the baryon number and lepton numbers, which are overall conserved. Lepton numbers are even conserved for each generation separately, except for long-distance experiments with the phenomenon of neutrino oscillations. Have fun with particle physics and see you in the next video.